Welcome to Chapter 6, Electronic Structure of Atoms, Part 1, where we're going to talk about Section 6.1, the wave nature of light, and 6.2, quantized energy and photons. So this whole chapter really discusses electron structure, the arrangement of the electrons, and the energy of the electrons. And we're going to start off talking about the energy of the electrons, and then at the end, we'll talk about how they are actually arranged in the atom. So when we're talking about the energy of electrons, we have to kind of talk a little bit about waves first and understand a little bit about waves. Waves have wavelength, which you can see here is the distance between the peaks, and that is represented with this upside down y, which is called lambda. That means wavelength. Amplitude is how high it is, okay? So to understand the electron structure of the atoms, you must also understand the electromagnetic radiation spectrum, okay? And electromagnetic radiation moves as waves, and they all move at the same speed, which is the speed of light, which will be represented at c, okay? We already talked about the wavelength. Here is our lambda. So here we have two waves. Their amplitudes are the same, but their wavelengths are different. This one here has a long wavelength. This has a short wavelength. And the amount of times it moves up and down, or the cycles, or the number of waves passing a given point per unit time, is called the frequency. The more it moves up and down, the higher the frequency. So this is low frequency, and this is high frequency. Frequency is represented with this kind of, it looks like a V, but it's a Greek symbol that's called nu. That is the name of it. This is called nu. So for waves traveling at the same velocity, the longer the wavelength, the smaller the frequency. Long wavelength, low frequency. Short wavelength, high frequency. So wavelength and frequency, I'm using their symbols so you get used to them, are inversely proportional. So as one increases, the other decreases. And if we assume that this line here is going from 0 to 1 second, this wave has 2 cycles per second. And this one has 4 cycles per second. Frequency is measured in the times it goes up and down per 1 second. And you could use the unit hertz, which is abbreviated Hz, which is also equal to 1 over seconds. How many cycles over a second? Or you could write it as seconds to the minus 1. So here is an image of the electromagnetic radiation. We are mostly familiar with the visible spectrum because that's what we can see. And this little part here is the visible, so it is very small compared to the whole electromagnetic radiation. And you see it ranges from gamma rays all the way up to radio frequencies. So if you look at this, as you go from left to right, your wavelength is increasing. But as you go this way, your frequency is increasing. So if you were right here, you would have a long wavelength, but a very low frequency. And over here, you would have a short wavelength, but a high frequency. And as I said before, all of this whole spectrum here, all of it travels at the same speed. And that is called the speed of light, which we call c, and it is 3 times 10 to the 8 meters per second squared. And c is what you get when you multiply wavelength in meters times frequency in 1/seconds. Then you get meters over seconds. See that? That is equal to the speed of light. So it's kind of fascinating if you think about it. All light travels at the same speed. And actually, light travels faster than sound. That's why they say when you see lightning, you count until you hear thunder, and that tells you how far a storm is, because the light will reach you faster than the sound of the thunder. Because actually, the lightning and the thunder are happening at the exact same time, right where the storm is. So here are some common wavelength units that you need to get familiar with so you could convert. When you are using this C equals lambda nu, lambda has to be in meters. So if I give it to you in angstroms, you need to know how to convert it to meters, or nanometers, or micrometers, millimeters, centimeters, kilometers. Okay, so become familiar with these conversions, because you might have to know them to solve your problems. So as we saw on the previous slide, there are many types of electromagnetic radiations, ranging from gamma all the way to radiant. And they all have different wavelengths and energies from each of them. And the typical wavelength unit varies based on the length. So that's why you have to know these prefixes here. There are some electronic properties that are not explained by waves. And there are 3 in particular that we're going to learn about in this chapter. The first one is, have you ever seen a hot piece of metal glowing, giving off light? So the emission of light from hot objects, this is called black body radiation. Why is it called black body radiation? Because before that object was hot, it wasn't giving off any light, so that was considered like dark or black. Then you heat it up and it glows and light is emitted. That's called black body radiation. And the different colors kind of give you an idea of the temperature. Another type is called the photoelectric effect, and this is actually pretty cool. When you shine light on a piece of metal, it will emit electrons. And when electrons are emitted, it actually has a current, an electrical current. So you shine light on a piece of metal and you make electricity. This is how solar panels work. They take the light from the sun and they generate electricity, which then either goes back to the electrical company or is stored in batteries. And the third type is the emission of light from excited gases. And this is when you see your neon lights. Inside that glass tube is neon gas. They excite it and it emits light. And this is called emission spectra. So what is the nature of energy that is generated from our electrons? Well, the wave nature of light does not explain how an object can glow when its temperature increases. Because why doesn't it glow all the time? Why does it only glow when you reach a certain temperature? Well, Mr. Planck here explained it by assuming that light energy comes in these packets called quanta, or the singular form called quantum. And you might have heard of quantum before. So here is a good analogy. A continuous amount of energy would look like you walking up a ramp. But that's not really what happens. There are these steps or distinct packets of quantized energy. So if you want to get from step 3 to step 4, you need to apply this much energy. If you apply less than that, you're not going to make it up the step. Okay, and the same thing happens with our electrons. When they are hit with a certain amount of energy, if the energy is less than what this like step would be, then nothing would happen. But if it's more than that, then the electron can actually jump up to the next level. And you might remember this from your Chem 1 days. You excite the electron, and then when the electron falls back down to the lower energy levels, it releases light. And that light is called a photon. So the photoelectric effect, here you have your metal, and you are shining photons, which are pieces of light, at the surface. If the energy of that light is high enough, it will emit electrons. So electrons are jumping off the surface of the metal. If the energy of this light is too low, nothing will happen. So you need to have enough energy to kind of eject the electrons off of the metal. So this photoelectric effect will not occur if the light is less than the threshold frequency. So see here, you have this H times the frequency. So your light has to have a high enough frequency to eject the electrons. And the equation that he came up with, Einstein, is that energy is equal to H times the frequency. And this H is Planck's constant. Which is right here. And nu is frequency. So now we have two equations. We have our energy equation and we have our speed of light equation. So therefore, if you know the wavelength of your light, you can calculate the energy of one photon. Remember, that's a packet of light. Okay? Or if you know the wavelength, you can calculate the frequency. So by using these equations, manipulating them, you could calculate the wavelength, the frequency, or the energy. Remember, c is the speed of light, which is 3 times 10 to the 8th. Lambda is the wavelength in meters. So if it's giving in other units, you have to convert it to meters. V is the frequency, which is 1 over seconds or hertz. And E, just like our last chapter, is measured in joules. And Planck's constant, become familiar with this number, is H. So let's try some examples. Using the two equations on the previous slide, come up with a relationship between energy and wavelength. What is the frequency of radiation whose wavelength is 10 nanometers? And what is the wavelength of radiation that has a frequency of 7.6 times 10 to the 10? So pause this video and try to solve these problems right now. Okay, so let's see if you got it right. So you have to remember that C equals lambda nu and E equals H nu. What variable do both of these have in common? Frequency, right? And we want to come up with a relationship that relates energy and wavelength. So if I solve this first equation for frequency, I get that it's C over lambda. So now wherever I see a frequency, I could put C over lambda. So E is H times C over lambda. So this is your relationship. Okay? So interesting to note, if you look at this equation here, the higher your frequency, the larger your energy. So they are directly proportional. And if you look at this equation here, the higher your wavelength, the lower the energy. They are inversely proportional. All right, let's try number 2 now. What is the frequency? So we're looking for frequency whose wavelength is 10 angstroms, and an angstrom is 10 to the minus 10 meters, or you could write this as 1 times 10 to the minus 9 meters. So what equation has frequency and lambda in it? Well, c equals lambda nu. And we know c is the speed of light. So that's a constant. So I don't have to give you that. You should know that. So if I want to rearrange this and solve it for frequency, frequency is c over lambda, which is 3 times 10 to the 8th, divided by 1 times 10 to the minus 9. Now it's important you put parentheses around this bottom one when you're putting it in your calculator so that the order of operations don't mess up your calculations. When you do that, your answer is 3 times 10 to the 17 hertz. A gut check, when you're dividing exponents, you subtract them. So 8 minus a negative 9 gives you a 17. So then you know you're in the right range here. And 3 divided by 1 gives you 3. So now they're asking, what is a wavelength if the frequency is 7.6 times 10 to the 10 inverse seconds? Again, we know c is the speed of light. So now, and this is our equation. Notice how I'm listing all my information, writing the equations, then solving the equations for the variable that I'm interested in. This is a very good practice when you're doing word problems. And I highly suggest you do this. And your wavelength is 3.9 times 10 to the minus 3. Since this had 2 sig figs, our answer has 2. So in summary, what are the equations for light? Well, there's c equals lambda nu and E equals H nu. You should know what C is and H, so start practicing remembering those. How are frequency and wavelength related to each other? Well, if wavelength is long, your frequency is small, right? So they are inversely proportional. What is a packet of energy light carries called? So what is the name of that packet of energy that light carries? And that is called a quantum. A piece of light, one little piece of light, is called a photon. Well, that's it for part 1. If you have any questions, let me know.